Welcome to lecture number 22 of the course Computational Hydraulics. We are in module 2 numerical methods, and this is unit 18 mesh free method, moving least squares method. Learning objective: to discretize ordinary differential equation using moving least squares method. What is this moving least squares? In our polynomial interpolation, we have represented our function in terms of P transpose A, and depending on the basis we have different kind of approximations, and we can utilize the A values which we can get from the inversion of the polynomial matrix based on available function values for construction of weight functions. Now, we can use this first step, and then again we can use our basis for moving least squares. Now, in local domain for arbitrary point x, we can have this phi x xi, where xi is for this polynomial and Ax is our original vector, A vector. Now, in this case MLS approximation or moving least squares method approximation is based on minimization of weighted residual for variable Ax. So, Ax is variable. Previously we have got the Ax value based on inversion of matrix. Now, we can represent it as minimization problem. So, in this case we have a definite structure for this omega or weight function for minimization. This h is the approximated value based on polynomial approximation, and xi is the original value for that point. So, if we consider any arbitrary point, so obviously if this is our original function value and this is constructed polynomial. So, obviously we will try to reduce the difference between these two values. Now, in this minimization problem, the first condition is that if we differentiate this j, which is the objective function for this minimization problem with respect to variables, the first order derivatives should be 0. So, in this case if we replace our original form from this equation, then we can write this equation as P transpose xi Ax, and this is our again function value for phi xi, and given this omega x minus xi, which is given function for this particular problem. Now, minimization condition, j should be differentiated with respect to A means for all A values. Now, in this case, if we differentiate with respect to A1, A2, then we will get system of equations, because individually if we equate with 0, so we will get number of terms for this particular derivative. So, this linear system is Ax into Ax, where your A is again represented in terms of W x minus xi, p xi and p transpose xi. So, in this particular case, we are writing this and B on the right hand side, this is B1, B2 to Bns, Ns again number of points in the support domain, and Bi is our omega x minus xi p xi. So, this is for one particular B, that means Bi, if we write B1. So, obviously, in this case this is first point x minus x1 p x1 like that, but p is again vector in this case. Now, in this case this phi s is column vector. So, we have phi 1, phi 2 to phi ns in this case. So, with this we can calculate A. So, we can take inverse of A into B, and phi is the value which is available in the neighborhood of the given point. So, in this case we can represent this omega I, this is x into phi I, number of points in the support domain, and omega I, this is can be represented as p transpose A Bi, because we are considering only one I in this case. So, the matrix form in this case is our W transpose x phi s W1 to Wns. That means wait for all the points available in the support domain. So, we can utilize this concept in case of our one dimensional problem, but one problem is there. The problem is associated with the derivative calculation of W. In previous case of polynomial interpolation, the calculation of derivative is simple, but in this case this is somewhat different. So, let us represent this W transpose x p transpose x A inverse B, and we need to differentiate this whole thing this whole thing with respect to x. So, let us reduce this full expression into two parts. That is, first term, let us write it as gamma transpose. That means gamma transpose equals to P transpose A inverse. Now, if we take transpose of this one, so obviously this will be A inverse and this is P. In this case, we will have gamma and there will be change of site. So, we can write this A gamma equals to P. So, this is our form. Now, we know that how to calculate derivative of this. So, first part, this is A gamma x and this is P comma x. This is represented as A comma x gamma y. So, this is nothing but full derivative and we can write it into parts plus A comma x into gamma, and we can directly equate it with P comma x and we can get this expression. Now, gamma x or first derivative of gamma can be directly calculated with A inverse this whole thing P comma x minus A comma x into gamma. So, this is all about first order derivative of gamma comma x, first order derivative of gamma, that is gamma comma x. Now, similarly we can write the same thing. So, if we have A gamma comma x equals to P comma x A comma x into gamma. Now, in this case we can again differentiate. That means, if we have A gamma and twice differentiate the same thing. So, this is A comma x into gamma plus A gamma comma x, and this whole thing is again comma x. This is comma is our first derivative. So, this is A comma double x, this is gamma plus A comma x gamma comma x, plus from the second term we get A comma x gamma comma x plus A gamma comma double x equals to P comma xx. So, from this one we can simplify A comma xx gamma plus 2 A comma x gamma comma x plus A gamma comma double x equals to P comma xx. So, from this one we can directly calculate the second order derivative of gamma x x like this. So, this is all about calculation by indirect method. We are not directly differentiating the w with individual terms, we have transformed it with a new variable gamma, and we are calculating the derivative of that function. So, first and second order derivatives can be calculated like this. So, now the full thing is gamma transpose comma x, this is our first derivative and this is second derivative. We already know the value of gamma comma x and gamma comma x x. We can utilize that value for calculation of first and second order derivative of our weight functions. Now, in this case again let us consider our original problem. Original problem is one dimensional groundwater flow equation. Mathematical conceptualization is in terms of second order derivative, and a support domain we can have 2, 3 or number of points. In this case, using a mesh free shift function, we can represent it like this. Now, in this case derivative can be approximated like this. Now, derivative calculation we have already performed using that by introducing a new variable gamma. If we have ns number of nodes present in the local support domain, obviously we should include all points. Now, in this case our calculation is not straightforward like our finite difference or mesh free methods of polynomial interpolation. If you have ns number of nodes present in the local support domain, if interior nodes equation is not that kind of simplified form. Only thing is that problematic term is this one, because it involves the calculation of our shape functions. So, in this case polynomial basis of order 2 can be used. So, if you use polynomial basis of order 2, that means we are using in this case 1 x square. So, let us say that L is the index for support domain or points in the support domain. So, L equals to 1 to ns, that means all points in the support domain. We can directly write this or if you multiply these two terms, we can directly write this thing. Problem is with the structure of this omega x minus xl. Now, we need to define the structure of this one, because this is a given function for our problem, only a was a variable. So, BL, again structure of BL for any arbitrary L, that is x minus xl 1 xl square. Now, characteristics of this weight function omega x minus xi, should be greater than equals to greater than 0 within support domain, should be 0 outside support domain, and is sufficiently smooth. That means smooth function is required for this weight calculation, and this omega x minus xi, this one is monotonically decreasing from point of interest towards boundary. So, if we have x minus xi by xr, this is our radius. So, we can use different weight functions. So, in this case, first representation is in terms of cubic spline. So, if r greater than 1 means outside support domain. So, outside support domain it is 0, from Ri, that is Ri bar equals to x minus xi by Rw, this is normalized one, radius starting from 0 to 1. From 0.5 to 1 we have one variation, and below this 0.5 we have another kind of variation. So, this is continuous function. Again we can use this weight functions for calculation of our problems. We can have exponential function where alpha is some defined value, Ri again greater than 1, this is 0, and within this domain or Ri less than equals to 1, we have this exponentially decaying function. That means at point of interest this is equal to 1, a to the power 0 equals to 1, and then exponentially decaying value. If we have quartic spline, in this case again we have within support domain, it is defined in terms of some function which is varying with Ri, and outside support domain again this is 0. So, these three are a typical example for choice of weight function or for the MLS approximation. So, we can see that in our MLS approximation we are not getting any explicit form like polynomial interpolation thing. In case of polynomial interpolation we got our two things, that is for interior points and for boundary points, two equations or expressions which are similar to finite difference method. But in case of MLS we are not getting any explicit form of the equation. Indirectly we need to solve the equation, and then only we can get the solution out of this method. Thank you.